I'm lecturer in physics. Present I am working in TTWRDC Women's Rajana Sirsilla. Okay, in this lecture I am going to discuss about band theory of solids. Okay, what is band theory? Okay, what is band theory? Okay, in this band theory is explains about the quantum states. Okay, the electrons moving inside the metal. Okay, the electrons is moving inside the metals. The way of electrons and the behavior of electrons is explained in this band theory. Okay, the way of electron and the behavior of electrons is explained in this band theory. Okay, then what is the band theory of solids? Solids are the three types of materials. Solids are three types of materials, that are insulators, conductors and semiconductors. Insulators, conductors and semiconductors, these solids are classified. Okay, these three materials, the way of electron or the behavior of electron is explained in this band theory of solids. Okay, let us discuss about the valence band and conduction band. Okay, let us discuss about the valency band and conduction band. Okay, this valency band is the highest energy band. Okay, the highest range of electron energy band. This valency band is completely filled with electrons. This valency band is completely filled with electrons. Okay, at absolutely zero temperature. Okay, at absolutely zero temperature, this band, okay, at absolutely zero temperature, this band is called as the valency band. Okay, next let us discuss about conduction band. Okay, this conduction band, okay, this conduction band is unfilled energy band. This conduction band is unfilled energy band and empty band also. Sometimes this some materials, this conduction band is partially filled band. Okay, this conduction band is unfilled energy band. Some materials, this is empty band, and some type of materials we are using in this that is partially filled conduction band. Okay, the next valency band after this, next conduction band is highest energy band. Okay, valency band after highest energy band is conduction band. Okay, let us discuss about the band gap and forbidden energy gap. Okay, let us discuss about band gap and forbidden energy gap. Okay, what is forbidden energy gap? The separation between the valency band and conduction band. Okay, the separation between the valency band and conduction band is called as forbidden energy gap. For example, if the electron is moving from valency band to conduction band and the electron is transferred from valency band to conduction band, okay, some external energy is required. Okay, some external energy is required in this forbidden energy gap. Okay, that external energy, okay, that external energy is equals to the forbidden energy gap. That external energy is equals to the forbidden energy gap. Okay, next let us discuss about the band theory of solids. Okay, let us discuss about band theory of solids. Okay, this band theory of solids, depending upon the nature and depending upon the forbidden energy gap, this band theory of solids is classified into three types. Okay, depending upon the nature and depending upon the forbidden energy gap, these band theory of solid classified into three types. What are they? First one is insulator, and next second one is conductor, and third one is semiconductor. Okay, for insulators, semiconductors and conductors. Okay, let us discuss about insulator. Okay, what is insulator? What is insulator materials? Okay, the substances are the materials the electric current does not passing through that materials, does not allow the electric current passing through these materials, is called as, that materials all are called as insulators. Okay, the electric current, the substances are the materials which do not allow the electric current passing through that materials. All are called as, all materials are called as insulators. Okay, let us discuss the examples in this figure. Okay, let us see this figure. Examples. Okay, what are the examples here? In this one, glass, plastic, rubber, ceramic, wood. Okay, glass and plastic, rubber, ceramic, wood and paper. Okay, these all are the examples of insulator materials. Okay, these are all the examples of insulator materials. Okay, now let us discuss about the forbidden energy gap in this insulator materials. Okay, this is the forbidden energy gap in this band gap in insulator materials. Okay, first of all let us consider here valency band and conduction band. Okay, valency band and conduction band. Okay, here this valency band is completely filled with electrons. This valency band is completely filled with electrons. Here the conduction band is empty band. Okay, the valency band is completely filled band and conduction band is empty band. Okay, here the band gap, the forbidden energy gap is more. Okay, the large forbidden energy gap between the valency band to conduction band, that is 5 electron volts forbidden energy gap is there in insulator materials. Okay, so due to high large forbidden energy gap, the electrons cannot jump from, or the electrons cannot move from valency band to conduction band. Okay, the electrons, due to large forbidden energy gap, the electrons cannot move from valency band to conduction. Okay, the electrons cannot jump from valency band to conduction band. Okay, due to this fact, the electrons are, due to this fact, the electrons are, okay, the valency electrons are, the electrons are very tightly to their parent atoms, so the electrons are cannot move from valency band to conduction band. Okay, in these insulator materials. Okay, when the temperature is increases, okay, when the temperature is increases in this insulator materials, the resistance power is also increases. The temperature is increases in these materials or insulator materials, the resistance power is also increases. So in this insulator material, in this insulators, this is called as positive temperature coefficient. Okay, positive temperature coefficient. Next let us discuss about the conductors. Okay, what is conductors? The conductor materials are, electric current is allow them, or the electric current passing through these materials. Okay, the electric current passing through these materials are called as conductors. The electrons freely move from one atom to other atom. Okay, these materials are all called as conductors. For example, let us discuss examples of conductors. Okay, aluminum, gold, copper, silver, These are the examples of semiconductors. These figures, aluminum wire, copper wire. Okay, these are the examples of conductors. Okay, let us discuss the band gap or forbidden energy gap of conductors. Okay, let us see here. This valency band is completely filled. Okay, then conduction band is also filled. So the forbidden energy gap. Okay, no forbidden energy gap between the valency band to conduction band. Okay, here no forbidden energy gap between the valency band to conduction band. So the electrons are easily overlapping to the valency band to conduction band. The electrons are easily moving from valency band to conduction band. Okay, next the from important point in this conductors. Okay, here the electrons conduct in conductors, the current flow, the flow of electrons, the moving of electrons from valency band to conduction band, that is considered as the current. Okay, in the conductors the electrons are moving from the valency band to conduction band, that is called as current. Okay, next let us discuss about the history of semiconductors. Okay, let us discuss about the history of semiconductors. Here in the year of 1821, in the year of 1821, Thomas Seebeck, okay, Thomas Seebeck discovered the semiconductor properties. Okay, in the 1833 year, in the year of 1833, Michael Faraday reported on conductivity temperature is depends upon the semiconductors. Okay, dependence of semiconductors. Next, in the year of 1875. Next, in the year of 1875, Werner von Siemens invented the selenium photometer. Invented the selenium photometer. Next, in the year of 1878, in the year of 1878, Alexander Graham Bell. In the year of 1878, Alexander Graham Bell is used this device of wireless optical communication. Wireless optical communication is discovered Alexander Graham Bell in the year of 1878. After that, in the year of 1907, okay, in the year of 1907, Ron demonstrated the first LED bulb invented. Okay, after that, in the year of 1940, in the year of 1940, Russell Ohl is discovered the PN junction diode. Okay, these semiconductor materials are discovered in the 19th century only. Okay, maximum. Okay, now let us discuss about the semiconductors. Okay, let us discuss about the semiconductors. These semiconductors are the metals whose resistivity, the semiconductors are the metals whose resistivity in between the conductors and insulators. Okay, conductors and insulators is called as the semiconductor materials. Okay, the resistivity, electrical resistivity in between the conductors and insulators, that type of materials are called as semiconductors. Okay, then what are the examples of semiconductor materials? Okay, silicon and germanium. Silicon and germanium are the examples of semiconductor materials. Okay, then what are the resistivity in between the conductors and insulators? That is 10 to the power of minus 4 ohm centimeters to 10 to the power of 3 ohm centimeters. This is the room temperature semiconductor resistivity. The resistivity in between the semiconductors, that is 10 to the power of minus 4 ohm centimeter to 10 to the power of 3 ohm centimeters, and this one is the room temperature. Okay, at low temperature the valency band is almost filled. Okay, at low temperature the valency band is almost filled, or the conduction band is almost empty band. Okay, in this semiconductor forbidden energy gap is less forbidden energy gap between the valency band to conduction band. That forbidden energy gap is 1 electron volts. Okay, very small, that is 1 electron volts. Okay, in the semiconductors behaves like an insulator at very low temperature. This is most commonly used semiconductor. That semiconductor silicon band gap is 1.21 electron volts and the germanium band gap is 0.785 electron volts. Okay, the semiconductor silicon band gap is 1.21 electron volts and the germanium band gap is 0.785 electron volts. Okay, next let us discuss about the semiconductors examples and semiconductor devices and semiconductor band gap diagram. Okay, in this figure the semiconductor devices are the operation amplifier. Okay, operation amplifiers and integrated circuits. IC means integrated circuits, and transistors and resistors and capacitors and diodes. These all are the semiconductor devices. Okay, where ఇవి మనం ఎక్కడెక్కడ యూజ్ చేస్తామో let us see here. Next forbidden energy gap or the band gap diagram. Okay, in the valency band, okay, is completely filled. Conduction band is empty band. Okay, so here the forbidden energy gap is less, or the forbidden energy gap very small. So small forbidden gap energy, so the electrons are moving from valency band to conduction band. So in this figure one electron is jumped from valency band to conduction band. Okay, in this valency band, this is the red figure, this is the vacancy hole. The electron is moving from valency band to conduction band. So in this valency band this is considered as vacancy hole. Okay, this is about the semiconductor band gap diagram and semiconductors devices. Okay, where the semiconductor devices are, what is the use of semiconductor devices, let us discuss. Okay, resistors. Resistors are the two terminal devices and electronic circuits. The resistors are used to reduce the current flow, then resistors we are using. Next transistor devices. Okay, transistor devices are used for amplifying and controlling and generating the electrical signals. So on that place we are using transistors. Next integrated circuits. Okay, next integrated circuits, essential programmable read-only memory. Okay, the ROM process and the computers, the ROMs, we are using integrated circuits. Next diodes. These diodes are the two terminal devices. Okay, these diodes are two terminal devices. At the low resistance and one direction and the high resistance direction, two terminals we are using. One side is low resistance and another side is high resistance. Okay, next capacitors. Okay, this capacitor devices is used for stores the electric charge in electric field. Okay, these capacitors are used for store the electric charge in electric fields. Okay, this is the use of semiconductor devices. Next okay, the conductors, semiconductors, insulators, these band gap diagrams compare. Okay, compare these band gap diagrams. Okay, first one is the conductors. These red color is completely filled with electrons. This is considered as valency band, and blue color, this is considered as conduction band. Okay, this valency band is completely filled. Okay, in the conductors no forbidden energy gap between the valency band to conduction band. Okay, here the electrons are easily moving from valence band to conduction band. Okay, next semiconductors. Second one is semiconductors. Okay, this total red color is filled with valence band with electrons, and blue color is conduction band. Here small forbidden energy gap between the valence band to conduction band, that is 1 electron volts. So 1 electron is moving from valence band to conduction band. In this valence band, this is considered hole. Okay, next let us discuss the insulator band gap diagram. Okay, next here in this valence band, this is completely filled with electrons, and in the conduction band, that is total empty band. Okay, here the large forbidden energy gap between the valence band to conduction band, so the electrons cannot move from valence band to conduction band. Okay, that is the forbidden energy gap in this insulator material. That forbidden energy gap is 5 electron volts. Okay, this is the energy band gap diagrams in solids. Okay, let us discuss about the types of semiconductors. Okay, types of semiconductors. These types of semiconductors are two types. Okay, what are there? Intrinsic semiconductors and extrinsic semiconductors. Intrinsic semiconductors and extrinsic semiconductors. These intrinsic semiconductors are pure form of semiconductors. These intrinsic semiconductors are pure form of semiconductors, and extrinsic semiconductors are impure form of semiconductors. Okay, intrinsic semiconductors are pure form of semiconductors, extrinsic semiconductors are impure form of semiconductors. Okay, let us discuss. Okay, again these extrinsic semiconductors are classified into two types depending upon the impurity. These extrinsic semiconductors are again divided into two types. What are there? First one is N-type semiconductor, next one is P-type semiconductors. Okay, now let us discuss about the intrinsic semiconductors. Okay, let us discuss about the intrinsic semiconductors. Okay, these intrinsic semiconductors is extremely pure form of semiconductors. These intrinsic semiconductor is the pure form of semiconductors. This is called as intrinsic semiconductors. Okay, then what are the examples of intrinsic semiconductors? Silicon and germanium. Okay, silicon and germanium are the examples of intrinsic semiconductors. Okay, these both silicon and germanium are the tetravalent nature. Okay, these both silicon and germanium are the tetravalent nature. So here let us see this figure. Each 4 electrons, okay, each 4 electrons in this outermost shell in this figure. Okay, next each atom is shares with the 4 valence electrons in the neighbor atoms. Okay, 4 valence electrons in the neighboring atoms. So each atom is involved in the covalent bonds. So each atom is involved in the covalent bonds. Okay, at that room temperature. Okay, at that room temperature, due to thermal agitation. Okay, at that room temperature, these four, let us see here. Okay, at that room temperature, due to this thermal agitation, these intrinsic semiconductors sometimes behaves like a insulator. These intrinsic semiconductors sometimes behaves like a insulator. Okay, next these intrinsic semiconductors are at room temperature, few electrons due to thermal agitation get enough energy. Okay, get enough energy to break the covalent bonds. get enough the energy to break the covalent bonds. Okay, to break the covalent bonds. Okay, due to breakage of covalent bonds, okay, some free electrons, okay, due to thermal agitation at the room temperature, due to thermal agitation to get enough energy to breakage of covalent bonds. Okay, then what happened? The free electrons are developed. Okay, on that free electrons some holes is also developed, some vacancy holes is also developed in this intrinsic semiconductors. So the electrons are equals to the holes. Let us see here in this intrinsic semiconductors figure. Okay, these yellow dots are called as holes and blue color dots are called as free electrons. Okay, here free electrons are equals to the holes. Okay, there is a small band gap between the valency band to conduction band. So in this intrinsic semiconductors, number of free electrons is equals to the number of holes. Okay, number of free electrons is equals to the number of holes. Okay, next we are applying, when we are applying the voltage, then that voltage is also increases and the temperature is also increases, then the breakage of covalent bonds is also increases. So on the breakage of covalent bonds, so that generate the electron hole pair generation. That electron hole pair generation is also increases in this intrinsic semiconductors. Okay, then a number of free electrons is equals to the number of holes in this intrinsic semiconductors. Okay, one disadvantage is there in this intrinsic semiconductor, that is limited of electrons are there in this intrinsic semiconductors. Next, it does not conduct well with room temperature. Why this is disadvantages means, at that room temperature sometimes these intrinsic semiconductors it behaves like insulator. So the electrons does not pass, the electron does not allow the current, or the electron does not flow. Okay, the electron cannot move. So this is the disadvantage of intrinsic semiconductors. Okay, next let us discuss about the intrinsic semiconductors. Okay, let us discuss about intrinsic semiconductors. These extrinsic semiconductors. These extrinsic semiconductors are impure form of semiconductors. Okay, these extrinsic semiconductors are again called as intrinsic semiconductor plus impurity. Intrinsic semiconductor plus impurity is called as extrinsic semiconductors. Okay, these impure form of semiconductors, selected impurity is added to the intrinsic semiconductors. Some selected impurity is added to the intrinsic semiconductors. This is behaves like a extrinsic semiconductors. Okay, these extrinsic semiconductors are third group elements and fifth group elements. Okay, these extrinsic semiconductors are the third group element and fifth group elements. Okay, we are adding the impurities now. So the process of adding the impurity process to the semiconductors, that process is called as doping. Okay, that process is called as doping. Okay, then why we are adding that impurities means, to increase the number of charge carriers. Okay, why we are adding that impurities in extrinsic semiconductors means, to increase the number of charge carriers in the semiconductors. So we are adding some impurities. Okay, this is about extrinsic semiconductors. Again we are adding the impurities. So these extrinsic semiconductors are classified into two types. What are there? N-type semiconductors and P-type semiconductors. N-type semiconductors and P-type semiconductors. Okay, let us discuss about the N-type semiconductors. Okay, let us discuss about N-type semiconductors. The pentavalent impurity. The pentavalent impurity. Okay, let us discuss about N-type semiconductors. Okay, these N-type semiconductors are intrinsic semiconductors plus fifth group elements are called as N-type semiconductors. Okay, in these N-type semiconductors, pentavalent impurity means fifth group means pentavalent impurities we are added to the pure semiconductor means intrinsic semiconductors. This is called as N-type semiconductors. So in pentavalent impurity we are added to the pure semiconductors, that is called as N-type semiconductors. Okay, what are the examples of N-type semiconductors? That are phosphorus, arsenic, antimony, bismuth. Okay, these are the examples of N-type semiconductors. These N-type semiconductors are fifth group elements. Okay, these N-type semiconductors are fifth group elements. In this one, the phosphorus symbol is P. Okay, the phosphorus P is used as a impurity to the germanium crystal. The phosphorus P is used as an impurity to the germanium crystal. Okay, let us see this figure in N-type semiconductors. Okay, this is a germanium crystals, germanium and phosphorus is middle, like pink shade. Okay, here the phosphorus P is used as impurity to the germanium crystal. Okay, the phosphorus, these are the fifth group elements, means the 5 valence electrons. Okay, out of 5 valence electrons, 4 electrons are participate in this covalent bond. Okay, out of 5 electrons, 4 will participate in this covalent bond, 1 electron is left free. Okay, here the red color is a free electron. Okay, this phosphorus P is the pentavalent impurity atom. Okay, 4 will participate, then 1 is left free. Okay, at that room temperature, due to thermal agitation, due to breakage of covalent bonds, okay, due to breakage of covalent bond, like that few more electrons are also left free. Okay, the few more electrons are also left free. Okay, in this crystal, one electron is free and another crystal and left free, and one electron is left free. Next, so many electrons are left free. Okay, then in this N-type semiconductors, majority charge carriers are the holes and the minority charge carriers are the electrons. Sorry, in this N-type semiconductors, majority charge carriers are the electrons and the minority charge carriers are the holes. Okay, in the each impurity atom is providing one electron, extra electron. So the pentavalent impurity is called as donor impurity. So each impurity atom is providing one extra electron. So like that the pentavalent impurities, okay, is called as a donor impurities. Okay, next let us discuss about the P-type semiconductors. Okay, next let us discuss about the P-type semiconductors. What is P-type semiconductors? Intrinsic semiconductors plus third group elements. Intrinsic semiconductors plus third group elements is called as P-type semiconductors. The trivalent impurities are added to the pure semiconductors, means trivalent impurities are added to the intrinsic semiconductors, that becomes called as P-type semiconductors. Okay, that becomes P-type semiconductors. Then what are the examples of P-type semiconductors? That are gallium and aluminium. Gallium and aluminium materials are all examples of P-type semiconductors. These are the start group elements. Okay, in p-type semiconductors, here the boron is used as the impurity in a germanium crystal. And this boron is used as impurity in germanium crystal. Okay, let us see this figure. Okay, these are the germanium crystal, green color. These blue colors are the valency electrons. Okay, next here one white color hole is there here. That white color is considered as hole. In this boron is the trivalent impurity atom. Okay, in these third group elements, out of three electrons are participate in this covalent bonds. Okay, but one hole left free. Okay, out of three valence electrons is also participate, but one hole left free. Okay, like that, at that room temperature, these at that room temperature, due to thermal agitation, okay, due to thermal agitations, the like that, in this crystal one hole left free, next another crystal another hole left free, next another crystal, like that. In these p-type semiconductors, majority charge carriers are the holes and minority charge carriers are the electrons. Okay, majority charge carriers are the holes and minority charge carriers are the electrons in p-type semiconductors. Okay, then each impurity atom providing one extra hole. Okay, each impurity atom providing one extra hole. The trivalent impurity is called as acceptor impurity. In p-type semiconductors, the trivalent impurity is called as what? Acceptor impurity. In the n-type semiconductors, that called as, in pentavalent impurity is called as donor impurity. Okay, this is about the p-type semiconductors and n-type semiconductors. Okay, then next we'll discuss about the applications of semiconductors. Okay, what are the applications of semiconductor? Okay, in the semiconductors we are using in our daily life. Okay, for example, in our homes we are using rice cookers. Okay, in that rice cookers, the rice cook perfectly because of the semiconductor materials only. In that semiconductor materials, the temperature is increases and sometimes decreases. Okay, then the cook rice perfectly because of the semiconductor materials only. Next one, in our homes we are using air conditioners also. Okay, on that air conditioners we are using air conditioners, then that also the temperature is decreasing. Okay, the temperature is decreasing because of the semiconducting materials only. Okay, next we are using flat panel devices. Flat panel devices means computers, televisions, mobile handle devices. Okay, in the computers we are using ICs. Okay, integrated circuits, chips we are using in this flat panel displays, like that they are using computers, televisions, mobile handle devices. Okay, next high brightness LEDs. High brightness LEDs means solid state lighting, large display panels. Next automotive applications, LCD, backlighting. In this one also we are using semiconductor materials only. Next, imaging array sensors. Array sensors we are using in our daily life. We are using cameras. Okay, in our mobile phone is also we are using camera. Okay, like that is also we are using semiconductor materials only. Next, telecommunication. Okay, one person to another person communicate with telephone only. So on the telephones also we are using semiconducting materials. Next, wireless communication means internet. Wireless communication, internet processes also we are using semiconducting materials. Okay, next diode lasers, diodes, lasers. Okay, and that also we are using semiconductors. Next, smart cards. okay, memories, okay. In our mobile phone we are using smart card. Okay, that smart card is also one type of semiconducting materials we are using. Okay, let us see this figure. Okay, this is the use of semiconductors in the automotive forces. Automotives also we are using semiconductors. Next, robotics. Okay, robotics also we are using semiconductors. Next, energy efficiency, internets. Okay, wireless communication, that process also we are using. In the security purpose also we are using semiconductors. Next, aerospace, healthcare, in the CT scans, that is also we are using semiconducting materials. In the communication process also we are using, okay, chips, integrated circuits, integrated systems. Okay, we are using the silicon, we are using in these materials. Okay, these are the applications of semiconducting materials. Okay, thank you all.